Hello guys, so welcome back to our lecture 18. So we discussed so far one type of flip-flops, which is basically the D flip-flop, okay? And here is another two types in this, recording, the JK flip-flop and the T flip-flop. So uh, again, any derivation from SR is basically to avoid the forbidden state, but SR is our foundation, the gates that lead us to all of this. So JK and T flip-flops are, another modification for the SR flip-flop that again avoid the forbidden state. Okay. So in JK flip-flop, we can, construct it out of a D flip-flop. And remember, D flip-flop is basically a modification for the SR to avoid the forbidden state. By connecting the input with this configuration here. This circuit basically. Okay, so we have two inputs. D flip-flop has only one input. This guy has two inputs. And of course, this kind of input circuit, these two AND gates and the inverter and the OR, this combination will lead us to a flip-flop with different characteristics than the D flip-flop. Okay, and here is its symbol. As you see, it has two inputs, J and the K. And of course, it's controlled like any flip-flop with a clock, this clock in here. So as we see here, D is basically J Q bar. So this input here is Q bar. Look, it's come from Q bar. So the output of the first AND gate, this AND gate is J Q bar. For the second AND gate, the first input is K bar, and the second input is coming from Q. So the output of the second AND gate is K bar Q. So basically D is J Q bar plus K bar Q. Okay, and that's what basically will will determine the next state for the Q. This is called the input equation. D equal to JQ bar plus K bar Q is basically called the input equation. And when I say Q without mentioning the time, that means the current state. So we have here two symbols that we should know. When I say something of t, like x of t, for example, or q of t, whatever, let's make it q, because we're going to use q all the time. This means current value of q. When I say q of t plus 1 means q at the next cycle. Q value at the next cycle. Q of t plus 2 after 2 cycles, plus 3 after 3 cycles, and so on. Okay. So let's check here, what kind of characteristics we're gonna have when we have the D is connected to these two inputs in that way, JQ bar plus K bar Q. It will lead us to what's called characteristic table. We didn't see this characteristics table with the D flip-flop because it was obvious. I mean, it was really clear. But I'm gonna explain at the end what should be the characteristic table of the D flip-flop. Okay, so look at the characteristic table for this JK flip-flop, and we're gonna analyze it, after showing it. So when J and K are zeros, the first case here, there will be no change in Q of t plus 1. I mean, QT of plus 1 will be equal to Q of t. So here, this means Q of t plus 1 equal to Q of t. I mean, if the current J and K are zeros and the clock comes, okay, Q will not change. It will remain as it is. If it was 0, it will remain 0. If it was 1, it will remain 1. When J and K are 1s, then Q will be complemented. So Q of T plus 1 equal to Q bar of T. If now J and K are 1s, and the Q, for example, was 1, when the clock comes, it will be 0. If J and K are 1s, and J was 0, when the clock comes, it will be 1. It will complement. Then we have the reset and reset state, just like the SR flip-flop. So when J is 0 and the K is 1, this is a reset. Q will be 0. When J is 1 and the Q is 0, this is a set. So Q will be 1. So that's basically, you know, a very good modification for the SR flip-flop. So because you have the set state, you have the reset state, and you have the no change state or memory state, but then you avoided the problem of having both inputs are 1, like just what we see, you know, 3 videos ago when we started talking about the SR latch, okay? And you change it this, you modify this forbidden state to be memory as well. So you have 2 options for the memory. If you want to keep your current output and store it basically, then make J and K equal to each other. Can we determine this from the equation? We see that D is equal to J Q bar plus K bar Q. We saw that. Okay, this is the input equation. Good. So now I'm explaining how we could get this characteristic table, how we could know these characteristics. Now, we know that for the D flip-flop, from the previous video, it's a transparent flip-flop. Whenever you have something when the input will be coupled to the output when the clock comes. So let's now do the characteristic table for this guy. We didn't see it. Let's now do it. So the characteristic table for D flip-flop is as follows. Basically, you have D and you have Q of T plus 1. So if D is 0, QT plus 1 will be 0. If D is 1, QT plus 1 will be 1. That's it. You know, it's really easy. That's why we didn't do it, basically. Because we just explain it, you know, just orally. But here is it. Now let's apply what we have here. So basically, Q of T plus 1 equal to D. That's what this table is saying, this characteristic table. And this is called the characteristic equation. Which comes just from the characteristic table. It's not something new. So let's do that for the JK flip-flop. So we know that D is equal to, as I said, JQ bar plus K bar Q. Okay. So Q of T plus 1, remember this is a D flip-flop, so it's equal to D, just like as a characteristic equation here. Remove D and put its equivalent. It's JQ bar plus K bar Q. Then, you know, compensate by JK with the four combination 0, 0, 0, 1, 1, 0, 1, 1, and see what's gonna happen. So let's try J equal to K equal to 0. If we do that, so Q T plus 1 will be equal to J is 0, 0 Q bar plus K is 0 as well, so K bar is 1. So 1 Q, this is basically Q of T, of course. When I say just the Q, that means Q of T. When I say just the Q, that is Q of T, okay? Current Q. Let's try. So that's basically the first one. when both are zeros, Q doesn't change. I mean, Q of T plus 1 is equal to Q. Next clock Q is basically equal to the current clock Q. J equal to K equal to 1. Q of T plus 1 equal to. Let's compensate. J is 1 now. So 1 Q bar plus K is 1. So K bar is 0. 0 Q. Look. Q bar. Of course, it's Q bar of T. It will complement. If the J and K are equal to 1, then Q will be complemented. Let's try J equal to 1, K equal to 0. This is a set state. We should see that Q of T plus 1 is equal to 1, whatever Q is, Q of T. So Q of T plus 1 equal to J is 1. So this will be Q bar plus K is 0. So K bar is 1. So 1 times Q or ANDed with Q. So Q of T plus 1 is equal to Q of T plus Q bar of T. X plus X bar is 1. Set. Finally, the set state. J equal to 0, K equal to 1. This is a reset. We should see Q is 2 of T plus 1 equal to 0. Let's do it. So Q of T plus 1 equal to J is 0. So 0 Q bar plus K is 1. So Q bar is also 0. 0 Q. That's basically 0. Reset. Okay. That's basically, you know, the JK flip-flop. I just, you know, make a mistake when I said that we modified the SR flip-flop and make the forbidden state, which is 1-1, as a memory. You know, it's not a memory. It's a complement of the current memory. So if you have currently 0, it will be 1. If it was 1, it will be 0. But this has, you know, very good applications. I mean, you can find applications that, you know, we need such characteristics. Or such characteristics will make our you know, application easier to implement or with less hardware resources. The second type of third type, I'm sorry, of flip-flops is T flip-flop. The T flip-flop. T flip-flop is basically, again, a modification of SR flip-flop in which you avoid the forbidden state. And as we did with the JK, it was implemented over the D, which is a modification of SR. T now can be implemented using both JK flip-flop and D flip-flop. And that's logic, because JK is basically a modification of the D. So that's why you can have both implementations. Okay? And the idea is really easy. For either the implementation using D flip-flop or T flip-flop. If you're gonna use a JK flip-flop, just connect J to K. I mean, you're gonna use this, we're gonna use this same circuit, but just to connect these lines. So they're gonna be just one input, which is called the T. That's it. So let's remove, not to confuse you. Okay. So you're gonna get a JK flip-flop and just to connect J to and the K together. And that's of course will lead to a different type of characteristics. I'm gonna see it in a moment now. Or you can get a D flip-flop and it takes the Q. This is basically Q. This is Q bar. Okay. Then take Q and XOR it with the T. This input. Okay. So the output here is T XOR Q. D is equal to, or the input equation is D equal to T XOR Q. And that would lead to very, you know, good characteristics. So, but we can do it in a very easy way. Just look at the characteristic table of the JK flip-flop. In the T flip-flop, J is equal to K. Whatever you put on J, it will be copied to K. So basically, you reduced the characteristic table to 2 possible rows instead of 4, because you force J to equal to K. So you have, let's do it with another color. So you have only the first case in which j equal to k but equal to 0, or the fourth case in which j is equal to k as well but equal to 1 that time. So you reduced the table to just 2 rows. That's basically characteristic table of the T flip-flop. Look, when T is 0, which means j is equal to k is equal to 0, you have Q of T. Let's look here. Yes, Q of T. When T is 1, which means j is equal to k is equal to 1, you have Q bar of T, the complement of the current value of the output. Look, Q bar. Okay, that's basically the T flip-flop. So basically the characteristic equation is Q of T plus 1 equal to, look, you can do it in 2 ways, but of course, I mean you can get the characteristic equation from this implementation or from this implementation, but they must be the same at the end. I mean, when you reduce them, you're gonna get the same equation. Let's try by the first one. Q of T plus 1 equal to, here is the Q, okay? So we know that for the JK flip-flop, the characteristic equation is, we just learned it, it's J Q bar plus K bar Q. And of course, Q and Q bar is Q of T and Q bar of T. But we just, for short, we're gonna just write Q. We know that whenever we see Q, it means the Q of T. But remember now, we connected the J to the K. They become just one input, just one, which is T. So we're gonna remove J and K and put T. So T Q bar plus K bar, T bar Q. What is this? This is basically T XOR Q. We learned this many times. So QT plus 1 is equal to T XOR Q. The XOR between the T input and the current value of the output. And look at this one here. So for this is from the first one, the JK flip-flop. If we do it from the second one, the D flip-flop, we should get the same equation. Let's see. So we know that this is a D flip-flop. So we know that Q of T plus 1 is equal to D. We show that here. Look. And from that circuit in here, D is equal to what? It's equal to T XOR Q. Look, exactly the same 2 equations. That must happen, you know. Okay. Now let's, drive this characteristic table out of the equation in here. Okay. If T is equal to 0, for example, so Q of T plus 1 will be equal to 0 XOR Q. Okay, if we look at the equation in here, so T is 0, 0 times Q bar will be just 0, then 1, it will be Q. And when T is 1, Q of T plus 1, let's check. T is 1, so 1 Q bar, plus T bar. T is 1, T bar will be 0, 0 ended with Q will be just 0. So Q of T plus 1 is equal to Q bar. The second line here. Okay. Now one may ask, which one is better to use? Okay, or to design with. Look, for simplicity, I mean simplicity of analysis, or the simplicity of the design steps, the number of design steps. Maybe the D flip-flop is the easiest one to use, because whenever the clock comes, the input will be copied to the output. That's it. But from the hardware viewpoint, I mean the hardware resources, the complexity of the circuit implementation itself, this is depend on the application. We will see in the future when we design circuits using flip-flops, we're gonna see that there are many examples in which using T flip-flop is much better than JK or D. The easier one. And we're gonna see if we use the D flip-flop, the circuit will be bigger. Okay, but if we use T, for example, the circuit will be much smaller. Okay, so it depends on the application. That's why we have, these varieties. If one of them is always the best, then why we should study the others? Okay. Okay, guys, thank you very much for watching this video. And now it's time for PhD lesson. So stay tuned for it. Thank you. Bye bye.